A very good morning to all the participants who are joined, and I thank your humble self to be on time. So, uh, for this session, we have Dr. Udiya Bhatt K from NITK Surathkal. I welcome you, sir, for this session. So, without delay, we'll start the session with a brief introduction of the speaker, whom we are very much privileged to have on this session. Dr. Udiya Bhatt K did his Bachelor of Engineering in Metallurgical Engineering from NITK Surathkal in 1992. Formerly, it was known as KREC. He did his Masters in Metallurgy from ISC Bangalore in 1994. Then he had his MBA degree from IGNU New Delhi in 2002 in Marketing Management. Dr. Udiya Bhatt had his PhD from ISC Bangalore in 2008 for dissimilar metal welding. Dr. Udiya Bhatt has been involved in more than 16 research projects. He had more than 100 peer-reviewed journals being published. He had conducted more than 12 workshops, delivered more than 30 guest lectures, and had guided more than 18 PhD students, more than 40 master students, and has been heavily involved in UG projects as well. His professional career, he has been a project assistant in ISC Bangalore in 1994. From 1994 to 98, he has held deputy manager in KIFL Hospete, Karnataka. And from 1998, he has been associated with NITK Surathkal, where he is currently working as associate professor in Department of Metallurgical and Materials Engineering, NITK Surathkal. So we are very much privileged to have you for this session, sir. The session is over to you, sir.
Hello, good morning to everyone of you. Whether I am audible?
Yes, sir, you are audible, sir.
Whether the screen is visible?
Yes, sir.
I will go for full screen.
Okay, sir.
Hope it's now full screen.
No, sir. We are able to view the earlier slide itself. It's not full screen now.
Not yet.
Not yet, sir.
Then I have to stop sharing and do once again. I will do it for 1 minute.
Oh, sure, sir. Sure, sir.
Is it now or same problem? Hello? Hello, whether screen is visible now or
no, sir.
Only?
The same problem. So what I would advise is first go to your PowerPoint presentation mode and then
Okay.
start sharing that screen itself.
But then I'm not able to see that screen. That is the issue. I had experienced that.
Okay, sir.
I tried to do that, but then it was not getting shared. Okay, I'll try once again, another 1 minute.
Okay, sir.
How is the situation? Is it same thing or?
It is the same thing, sir.
I think we'll continue then. Is
Okay,
it
sir.
screen is visible?
It is visible, sir.
I think there is an echo.
Uh,
Whether some mic is on?
Sir, I think now.
Okay, looks better.
Okay.
Fine.
Sir.
Okay. Good morning to all of you. Hope it's audible, right?
Sir,
Good morning to all of you. Okay, fine. Good morning to all of you. It's my pleasure to be with you in this Friday morning.
Excuse me, sir.
On the
Sir, your slide
hello.
is cutting. Your slide is not complete, sir.
Not complete in the sense?
It is cutting from the lower side.
Sir,
Yeah.
Sir, go for the first option itself, that present the slideshow, but you can toggle between the windows, sir, holding Alt and Tab key.
Okay, 1 second.
Okay, share the presentation mode, and then you can toggle between the windows to know which screen you are sharing.
Whether a complete screen is visible now?
Yes, sir. Now it is visible. Go for screen sharing, sir. Go for presentation mode now.
Okay. Is the full screen is visible?
No, sir. No, sir. We are not able to see the presentation mode. It is still showing the PowerPoint mode.
Correct, but this is a full screen is visible here for me in the presentation mode. My question is whether a screen is fully visible, because earlier there was a problem of half screen.
No, sir. Now it is completely visible.
Okay. So hopefully you are able to see the font size.
Okay, sir.
Okay. Okay. Yeah, sorry for that initial issues. So good morning to all of you. I take this as my pleasure to be with you this Friday morning on the FDP organized by JNN College of Engineering Shivamogga on the theme of novel nanostructured magnesium based alloys for industrial and biomedical applications. And I'm especially thankful to Dr. Rajat Hegde and Dr. Parameshwaran for being in contact with various stages of interactions, and Mr. Chetan for a nice introduction. Thank you all of you once again. Okay, I have many friends at Jawaharlal Nehru College of Engineering, so I could not say no to this request of giving a lecture. Anyway, that is a small issue, and more thing is the technical thing which we have to be interactive. That's important. So my title of the talk is novel nanostructured ultrafine magnesium based alloys for lightweight applications. So in this I will try to discuss various concepts related to design of nanostructured materials, and in some cases when you say nanostructured it can extend to ultrafine grain size also, but focus is more on magnesium. What are the concepts in this getting nanostructured and ultrafine structured material, what are the mechanisms involved, and some recent developments. And at the beginning I want to be very clear that most of these technical materials are taken from internet sources. My contribution is limited. I work more on aluminum alloys rather than magnesium. Magnesium is my recent entry. So I have taken or I have borrowed heavily from the internet source. In this talk, which will extend for another 55 to 60 minutes, I will bring some concept of introduction to magnesium alloys. It may be a repetition, but it is essential for a smooth flow of in the later talks. Then challenges and opportunities in the magnesium alloy development with a link to getting nanostructured and ultra-fine grain material. So whenever there is a challenge, if you are ready to take a challenge, then there will be multiple opportunities. So we'll explore some of these opportunities. Then when we have an opportunity, of course, there should be a lot of technical input required. Then only we can use opportunities which is fruitfully. So there will be a couple of mechanisms which we have to deal. We will try to bring some of the mechanisms. So all these mechanisms are related to magnesium alloys, but then you will realize that understanding these mechanisms will help you even if you work in aluminum alloys, copper alloys, and steel. Some of these mechanisms. Yeah.
Another window is open in the upper portion. There is work together faster and easier. Just got it, make it option so that it will be removed.
1 second. Work together. Got it. Okay.
Yes, yes. Thank you.
Fine. So we'll talk about some mechanisms related to magnesium and magnesium alloys. But then this concept will be same even if you go for aluminum alloys, copper alloys. So if you are working in such areas, you can extrapolate this understanding. So that will be useful for many younger researchers. Then some recent developments as far as processing of magnesium alloys. I will consider one important development which is taken over the last 5 or 6 years, which is expected to solve many processing problems in relation to magnesium alloys. Finally, at the end, I will try to conclude by putting some of the highlights from this talk. So if you see this slide, you have a good number of components made from magnesium alloys. It may be camera casings, it may be automobile wheels, then it may be housings, so on. All these are made by magnesium. Okay, there are other materials also in market like castings and aluminum based alloys, but magnesium has a special place in this one because you can see they are all lightweight items, especially camera and wheels of sports car and etc., luxury cars and etc. They are all lightweight. But these things are all cast materials. They are used as cast. So the photos here reference to cast items. Whereas the screen here.
Good morning, sir. Sorry for the interruptions. Really very sorry, sir. Your volume is very low. Can you please increase your volume, please?
Sure.
Sir, and also you are in the content side, in the content slide, but you are explaining the next slide, sir.
Okay. Now, whether volume is increased? Hello?
Still,
Yes,
still low, sir. Sorry, but और भी little bit increase कर दीजिए, please.
Yeah, but in my screen it is showing 80% of total volume.
Ma'am, it is. Please check on your side, ma'am, whether the speaker is completely full volume.
Okay, sir. Okay. Thank you.
We are hearing it properly.
Okay, sir. Okay.
Okay. Now, are we saving a correct slide? So I'm talking about magnesium alloys using in the form of formed product. Previous slide, whether you are playing slide number 3, now I am talking about slide number 3. You can see the number also. I introduced that. So this is slide number 3. These are magnesium items used in the cast form. You are seeing slide number 3, right?
Sir, it is 4.
4, sir.
Whether everyone is seeing that 4?
Yes, sir.
Okay, now I am in the slide number 4. So this is magnesium alloys used in the form of wrought product. That means there will be a mechanical forming operation which could be rolling, it could be forging, it could be drawing, all those things. Compared to magnesium alloys used in the cast form, this is relatively a new entry in the materials world. So when you say wrought magnesium alloys, they are going to subjected to either some of the operations, one or more than one manufacturing operations other than casting. It may be rolling, it may be forging, all those things. This is an interesting topic for us. Can we manipulate mechanical properties of this material? Can we manipulate mechanical properties of wrought magnesium alloys? So if you see, this is the, are you able to see the cursor? On the right hand side top, so we have a stent. So stent is basically a biomaterial. It is used for removing blockages in our, either it may be blood systems or it may be our food channels, so on, or bile channels, so on. This is a metallic stent made using magnesium. These are the forged products, impellers with twisted blades. So like this, we have number of items which are formed items, which are wrought items using magnesium alloys. So moving to slide number 5. So important thing to note in the previous, that is slide 4, is all applications require higher strength and higher ductility. Then only the designers can use magnesium alloy instead of others. So the demand is high strength, possibly high ductility alloy. So we need higher strength without compromising or with improving ductility. This is an important target in the use of materials in automobile sector, materials in aerospace sector, to an extent materials in bio sectors also, biomedical sectors also. So we have to see how to increase strength of magnesium alloys. That is an important aspect. How to increase strength of magnesium alloys. So we are moving to slide 6. Are you able to see slide 6 now?
No, sir.
What slide you are in now?
There are slide 4 only.
Everyone is in slide 4?
Yes, sir.
Okay, then once again, sharing is the problem.
Yes, sir. Now it is, I think, better. We will be in this window itself, sir. It's good.
Slide 6 is you, are you seeing slide 6?
Yes, sir. Yes, sir.
Okay. I will try to remove this. Okay, fine. So if it is visible for everyone, no problem. Slightly increase the percentage. Okay. Is it more than screen? Is it cutting? Okay.
Okay, sir. Now it's visible, sir. Now it's proper.
What about other members?
Sir, it's okay, sir, because I can look onto it what exactly is visible. We will keep
Fine.
it this way, sir. It's fine.
Okay. Now this slide basically gives an information about usage of magnesium in terms of indicated by the research article. So when more research is going on, it means there is a more and more opportunity for the magnesium alloys to be used. So first thing is research article as an indication of how the trend for magnesium research is going on. Now this trend is basically driven by the possible use of magnesium alloys in structural applications in the domain of aerospace and automotive applications. So when you consider magnesium alloys in aerospace and automotive applications, two important things we have to consider is low density. Magnesium is having very low density compared to other structural materials. Then magnesium has high specific strength, that is strength per unit mass. Strength per unit mass of the material. Magnesium alloys have high specific strength. They are extremely low density. In fact, this low density helps in increasing value of specific strength. So this is a driving force lot of work. So the result is that you can see the increase in research articles. This is slightly old data, that means 2006 only you are seeing, but here you can see exponential growth. Same thing is continuing, so that is indicated by number of research papers in 2020. More than 3,000 research papers have come in essay index journals. Then there is an association called as magnesium research, which makes or which suggests considerable guidelines how to progress in the domain of magnesium research. It's an international body like Aluminium Association is also an international body. So it gives a lot of ideas where our policy decision has to be taken by the government. It gives trust like that. So some important parameters which may be some repetition also for you. Magnesium, as we said, it is one of the lightest material and it's the lightest structural material. So with a density of 1800 kg per meter cube. So this is about 50% less compared to density of aluminum. So 50% less. Now if you compare density of steel and magnesium, it is about 1/4. Steel is having 7,000 kg per meter cube. This is having 1800 kg. So 1/4. So lot of weight saving is possible if you use magnesium and its alloys. And if you consider alloying element for magnesium, alloying is very much essential because we have to manipulate properties. One is by passing through various mechanical operations, we can manipulate properties. Other one is by altering chemical composition. So how do you alter chemical composition of magnesium alloys? We have to have alloying elements. Some of the alloying elements are aluminum. So in the nomenclature of magnesium alloys, aluminum is indicated as A. Then zinc Z. So if you say AZ alloy, it is the aluminum zinc alloying element. Magnesium as a host, aluminum and zinc as the alloying element. Then we have manganese indicated by M, silicon S, copper C, rare earth E, zirconium K. So I am putting this information because later we will use some of these alloys. So if you say AZ31, it means aluminum is 3%, Z is 1%, remaining majority is magnesium. So this must be understood clearly. Now, if you see the crystal structure, magnesium has hexagonal structure, whereas your elements like aluminum, copper, they are all FCC structure, whereas elements like iron, chromium, they are all having BCC structure. So this brings an important difference in mechanical properties and mechanical processing. When you have an hexagonal structure, its symmetry is poor compared to FCC. So FCC has, or a cubic system has highest symmetry. Cubic system has highest symmetry. Hexagonal is less symmetrical, which means mechanical property in X direction is different, Y direction is different, Z direction different. Your modulus, like that properties, modulus, Poisson's ratio, everything is direction dependent. So that is another difficulty involved. Whereas if you consider cubic based systems like copper or aluminum, their properties in X, Y, Z direction is symmetric, isotropic materials. So because of this, the processing of magnesium alloys is slightly difficult. It is not as easy as aluminum. So many people go away from mechanical processing of magnesium because it is not that easy. So as mentioned earlier in the slides 3 and 4, earlier days magnesium was used as cast alloy. So these are some of the domains where magnesium was used, cast alloys. Now after the last 20 years, people are using magnesium alloys in the rod form. They are able to manipulate shape of the magnesium alloy. They are able to manipulate properties of the magnesium alloy. So rot means this beneficial nature is possible. So these are some of the alloying elements commonly found in magnesium alloys. So these are a couple of alloys, nomenclature AZ63, aluminum 6, Z3, AZ92, aluminum 9, Z2 or zinc 2. So this could be in a sand cast. So sand is the material for making mold. It could be AZ91 could be die cast, metallic die. Whereas another batch of materials like AZ31, see this difference. Alloy chemistry is different. So it could be AZ31, AZ62. Only difference is 2% zinc. This could be an extruded form or heat treatable form. You can manipulate properties like strength by subjecting it to proper heat treatment sequence. Okay. Then there could be other alloying elements like zirconium and thorium, which increases age hardening tendency, precipitation hardening tendency. Then elements like manganese increases corrosion resistance. Tin is an alloying addition for cast alloys. Tin increases castability. So these are common alloying elements. Now, some of the alloying element is very important because we are going to increase strength of the material using this as an alloying addition. But in this focus, in this talk, the focus will be on mechanical processing and how to improve strength, not on the alloying addition side, mechanical processing side. So this is a famous Ashby diagram. You can see magnesium is somewhere here. Font may be very small, I agree, but because the figure itself is a big one, no way we could make it larger. So magnesium alloys here. I am reading the font, magnesium alloys here. So you can see these are all the polymer areas. This is other alloys like zirconium based materials, copper alloys like that. So they have higher density. This is Young's modulus, y-axis is Young's modulus, x-axis is density. So we can see that magnesium alloy stands somewhere middle. So this is zirconium alloys. Then here tungsten is there, very high density. This is some of the ceramics like silicon carbide, silicon nitride. So you can see the relative position. Magnesium is somewhere here. Whereas this is majority is polymers. Their modulus is less, density also close to magnesium alloys. Okay, so what we are trying to say is magnesium alloy or magnesium has a good combination of density and strength, or Young's modulus in this case. The strength also will have a similar plot. Strength versus density will have a similar plot. Okay. Now we will move on to some of the challenges in getting nanostructured materials in magnesium alloy. Anyone has a question till now or any point for discussion till now?
Sir, what is Ashby diagram, sir?
It's a diagram between one is basic properties like intrinsic property, Young's modulus, and density. It can be extrinsic property like strength also, but then strength means it will be varying based on your processing also. Okay, so Young's modulus is independent of processing, so you have only 1 point. Density for a material only one value, so only 1 point.
Okay. Thank you, sir.
Okay, so like that we have combination of strength, density, Young's modulus, density. Like that is there. Ashby is a scientist who collected the data. It is not his original work. He collected data from various papers. He draws as a map. So for us it is very easy now because in one plot I have all the information. About 25 years back this was not available. So those days we have to select data for copper, data for tungsten like that. Now everything is available in a single plot. We know the relative positions of this material. Okay.
Yes, sir.
Okay. So talking about some of the challenges in getting nanostructured materials in magnesium alloy. Why nanostructured materials? Because we know as length scale of microstructural parameter becomes smaller and smaller, because of the Hall-Petch relation, strength increases. If you recollect, in one of the slides we said target is to increase the strength. So if you increase the strength, then material required becomes less. Volume of the material required becomes less. So very good opportunity for lightweight applications like sports utilities, then automobiles, aerospace. These are all the sectors where high strength is required, less weight is required. Now the challenges are processing of magnesium alloys at low temperature is difficult. But if you go to high temperature, magnesium has a problem of fire hazardness, fire catcher. So easily gets hot with the fire. So we need to process at low temperature. But then low temperature, it is a hexagonal based material, which means processing is very, very difficult at low temperature. So one side you have to reduce the temperature to prevent from catching fire. In another side, at low temperature, its processability is very, very poor because it's hexagonal. Okay, some more you are changing conditions to increase the temperature of processing so that this difficulty could be overcome. Then there are other problems. Dynamic recrystallization. So as material is being processed at high temperature, it will undergo recrystallization phenomena. It will undergo grain growth. So we may not able to get small grain material after processing at high temperature. So how to control this phenomena so that final microstructure is fine grain, preferably in the nanoscale grain or at least in the ultra fine grain. So that is a real challenge. If you are allowing recrystallization and grain growth, then the benefit of processing and benefit of having smaller grain size is not there. Then, whenever there is a recrystallization and grain refinement, formation of new grains and it will result in grain refinement, no doubt. If you prevent grain growth, it will be grain refinement. But then it's a HCP structure, which means there will be changes in the crystallographic texture. Different grains will be oriented in different directions. This is not a problem if you are talking about FCC based materials because X, Y, Z, they are all isotropic. Property along X, Y, Z is same. Whereas in this case, HCP structure, property along basal direction or basal plane, property along C direction, they are different. So if I have a unit which is oriented in different directions, then property will be different. Then how to control this texture? So you have to control it so that final material will have a desired set of properties, crystallographic textures. So these are some of the challenges in the getting nanostructured microstructure in the magnesium alloy. Now, if you consider aluminum alloys, especially aluminum alloys, lot of work is being done and is happening now also on the severe plastic deformation. So use of severe plastic deformation methods to get the nanostructure in the aluminum alloy. Now extending same concept, that is a severe plastic deformation, to magnesium alloy, there are other problems. What are the other problems in magnesium alloys? It is practically difficult to get uniform ultra fine grain microstructure with initial coarse grain. Later slides will see the photography of these things. If you have an initial coarse grains, say 80 micrometer, 100 micrometer initial grain size, practically difficult to get uniform fine microstructure. That is, we are talking about either less than 1 or very close to 1 micrometers. 0.6, 0.8 or 1.5 to, that is the microstructure scale we are talking about when you say ultra fine. Okay, we are talking about micrometer scale. Either 0.8, 1 or 1.52 micrometers, that will come under ultra fine. If it is 100 and less than 100, you will talk about nanoscale microstructures. So initial coarse grains means we are talking about grain size of 80 micrometer, 100 micrometer, or sometimes 200 micrometer. They are all coming under coarse grains. So how to get it? Practically difficult to get uniform microstructure, where scale of microstructure feature is 1 micrometer. Another problem is the development of microstructure depends on the initial grain size. If it is 20 micrometer, different type. If it is 100 micrometer, initial grain size different. Microstructure formation is depending on that grain size and the amount of strain being imposed. Are you talking about 0.1% strain or 10% strain or 100% strain? So amount of strain decides microstructure development. You will see some of these stories later. Part of this problem arises because magnesium alloys are considered as difficult to work material. Main reason for difficult to work means they are HCP material. Their slip system is much less than what is there in FCC, for that matter even in BCC. Because they are HCP, they exhibit poor formability, shaping into various shapes, forming into various shapes is difficult. They have limited ductility at room temperature. So this is the serious limitation which limits use of magnesium alloys, because we cannot make into various shapes. We have seen in previous slides the requirement of making into various shapes, sometimes thin, intricate shapes. So this is practically a serious limitation. Now, what people are thinking is, like in aluminum alloys, if we can go for a SPD, pure plastic deformation, no doubt, if it's successful, you will get ultra-fine microstructure. Some amount of ductility will be retained. So if it is successful, the magnesium alloys can be used in light weight applications. So that is the need of ours, so that magnesium alloys used successfully in applications like sports, automobile, and aerospace. So in the previous slide, we said magnesium alloys have poor processability or formability at low temperature. Now, how do we take this information? One possibility is SPD pure plastic deformation should be done at high temperature to prevent cracking. That is the one direction of working. But if you think about this, there are other after effects. So use of high temperature, no doubt fire is one question mark. Then other question, if we talk about intermediate temperature. If we talk about intermediate temperature, then use of high temperature promotes dynamic recrystallization. That means as metal is being worked, there will be recrystallization of strain-free materials. And when everywhere strain-free material comes, your benefit of cold working is not there. And if you permit grain growth of new grains, then benefits of smaller grain also reduced. So this is the problem of working with high temperature. So we have to control all these things. If we can do that, then pure plastic deformed materials can have beneficial properties of grain refinement, and if we can control the texture, the crystallographic texture also possible. Okay. So some of the factors which decide texture development in magnesium alloys are conditions of deformation, that is temperature, strain rate, total strain, then materials parameter, chemical composition, then initial texture. So they will decide what will be the final texture. The overall material behavior in terms of material strength and ductility, that's the bulk strength and ductility, is affected by change in texture. So you have to see that texture is changed in proper way so that the strength and ductility is maximum. So you will have more information on these things in this paper listed below. Now, what are the different SPD techniques being explored for magnesium alloys? So the techniques are similar to whatever being used in aluminum alloys or copper alloys. These are 4 important techniques being explored to get the ultrafine grain structure and nanostructures in magnesium alloys. I would say this is more commonly used. These are also used, but not to this extent. So people are able to get microstructure of the scale of 0.7 micrometer using ECAP after 8 passes by processing at temperature of 200 degrees Celsius. The successful processing without crack. So not room temperature, it is high temperature. So here we can prevent, at this temperature we can prevent fire hazardness with minimum control. But if you process at low temperature, then there will be cracking. So one is important is temperature. So you can see this is what ECAP die is. If you are not exposed to this one, this is simple die. So it will be, this is the sample will be here. There will be plunger. It will be forcing the sample here. It will come out like this. And there will be material deformation leading to nanoscale or at least ultrafine grain. So this is one sample you can see here, initial sample. This is after deformation. So the same shape is retained, only the edge we have to trim it. Edge is trimming. So there is a sample size limitation. We cannot bring large sample here. The cross section of the sample could be of different types, but there is a limitation. Cannot have any random or arbitrary shapes. This is a configuration for multi-axial forging. So you can see here ABC, 3 surfaces are identified. So first stage compression is from A direction. So it becomes flat now. It is not rotated, it is same orientation, only dimensions are getting changed because of the external force. Don't assume it is this rotated. You can see same size surfaces are identified. So like this, you are applying force from A, from B, C direction sequentially. So we can have a second cycle of forging once again by applying force along A, B, C. So 3 directions total make 1 cycle. But then you can realize this is not applicable for any sample. We need samples with planar surfaces. So this is another type of severe plastic deformation which could be used for magnesium alloys. This is accumulative roll bonding. So you can see big sample piece is there. It is cut into small pieces. Surfaces are cleaned, kept one over another, passed through the rods. So this is a stage of deformation. You can see as it passes through, there will be strong bonding, so the interface is gone. But then once again it has a limitation. The sample has to be in the sheet form. It cannot be any arbitrary shape. So each one has a benefit, but then they also have limitation. This is another type called as accumulative back extrusion. You can see here, this is the initial sample. So first stage, this is being pressed, plunger is being pressed. The second stage, so the spacer is being pressed, this is going up. Third and fourth is reverse, that is the bottom side. So finally we get a shape of this. So you can see here at this corner, this is the material flow. Material flow is indicated with this arrow mark, which means a large amount of strain is accumulated here. Large amount of strain is accumulated here. So this creates nanostructures in the material. So this is basically, you can see the extent of strain with these images. So anyone has a discussion up to this now? Okay. So as I mentioned, ECAP was relatively popular. I would say people have used more compared to other methods. Popular in the sense it is having problems like any other method, but still, if you see the research articles, number of people working on it, it has more in relation to other SPD processes. So severe multi-cracking was observed at low temperature, lower than 200 degrees Celsius. Now, how to minimize this cracking tendency? There are changes in the design. One is applying back pressure. So this is the back pressure plunger. So if you apply back pressure, the cracking tendency will be reduced. The second way is increasing the channel die angle. So this is the channel die angle here. So instead of having an angle like this, you make it more. Then lower corner angle, equivalent strain could be reduced. Channel angle, corner angle is here. This is channel angle, this is corner angle. You alter these numbers or these angles so that cracking could be reduced. So we can have more number of ECAP passes. Remember, more number of ECAP passes, you have a tendency for finer grains. That is a possibility, provided there is no recrystallization and grain growth. Lower temperature, recrystallization, grain growth is less. Using lower temperature can help in preventing recrystallization and grain growth, but then cracking is the problem. Changing in these parameters can reduce cracking tendency in magnesium alloys, which means I can use, instead of 200 degrees Celsius, maybe 180, 170 degrees Celsius. All of them can lead to more number of ECAP passes without cracks. So the final benefit is greater grain refinement. So finer grains, fine grains in the final stage, which means Hall pitch strengthening is more effective. There could be also other associated strengthening mechanisms like work hardening, because dislocation, entanglement will take place. So strength will be increased because of the multiple strengthening mechanisms. So processing at lower temperature is possible, which means I need not worry about fire risk that much. So worry on firing is less. Then when I have more and more ECAP passes, chances of having homogeneous transitions in microstructure scale is better. So homogeneous transition in microstructure is better. So all this will contribute for beneficial properties either in terms of mechanical property or safety or larger cross sections. So people have attempted this on couple of magnesium alloys and they are successful at lower temperature compared to this. So we are all talking about grain refinement, so that final material will have a smaller grain size, so that Hall pitch strengthening will come into scene. But the grain refinement in magnesium alloy is not equivalent to that happening in FCC metal. So there are some differences between grain refinement in magnesium alloys compared to that happening in copper and aluminum. The differences arise because, as I mentioned, magnesium alloys are HCP based materials. HCP based materials have less number of slip systems. So less number of slip system means their ductility or deformability will be less. Even these slip systems are limited to only basal plane, which means in other directions difficult to deform. In the case of magnesium alloys, the understanding of grain fragmentation, that is a bigger grain becoming smaller grain and smaller grains, is not that much accepted version of the grain refinement. It is true in the case of copper and aluminum, whereas in the case of magnesium, grain fragmentation is not very well accepted. So once you don't have an understanding of mechanism of grain refinement, other things are always questionable. So once understanding of grain refinement is not clear, exploiting this mechanism for magnesium is dangerous. It is difficult. So we need a better understanding of mechanism related to grain refinement. So we'll try to see whether we can do something there. Okay. So to understand the differences, we'll recap what is there in FCC metals. In the 1 or 2 slides, we'll recap it. The initial stages of training in FCC materials produces an array of elongated sub-grains aligned parallel to the primary slip systems. In FCC, this is easy because slip system number is large. I will show one micrograph. So you can see. So this is the initial grain as cast aluminium 5 zinc to magnesium. This is an aluminium alloy. We are talking about fragmentation or subdivision of grains in FCC metal. So aluminium 5 zinc to magnesium alloys. So this is after first pass. You can see after second pass, third pass and fourth pass. So you can see the fragmentation. These are all big grains becoming smaller grains. You can see the fragmentation, which is much clear in this fourth pass. This is also clear. So bigger grain becoming smaller grain. So you have to get this in a proper oriented direction. Microstructure have to be properly oriented direction, then only you can see that. So initial fragmentation takes place. Then with increase in strain, you have a large number of dislocations. Dislocations are getting generated. They will rearrange because happening at slightly high temperature, and continuously they get annihilated. So we can see the low energy dislocation barriers. So these are all the dislocations, large number of dislocations continuously getting generated and annihilated. This is once again aluminium 5% zinc to magnesium for comparison. It's not magnesium alloy, it is based with the aluminum alloy. So this is the grain boundary you can see here. This is after homogenization, this is after one pass. So large amount of dislocations are there. You can see very fine grains here. Very fine. You can see these are all individual patterns indicating they are all this is called as SAT pattern, selected area electron diffraction pattern. This is from single crystal. Then only you will get this dotted pattern. Whereas this is a ring pattern indicating the electron beam is interacting with multiple fine grains. So when you get a ring pattern, it's an indication of fine grains. Electron beam is interacting with multiple grains. Okay. And third stage, reasonably equous grains are separated by high angle grain boundaries are produced because of the continuous training of this material. So these are all extremely fine grains. You can see this is one grain, another grain like that. So the scale is 1 micrometer. This may be 100 or in that range. Anyone has a question here? Now, this is aluminum alloy. In contrast, in magnesium alloy, what happens? The microstructure is inhomogeneous. Even in the initial stages of ECAP, we get a inhomogeneous microstructure because different grains are oriented in different directions. Only few grains are oriented along ECAP direction. So properly oriented grains will undergo fragmentation, whereas not properly oriented grains will not undergo fragmentation. So in such grains, those grains which are deformed, recrystallization will start early because large amount of slip will be there, large amount of dislocation will be there. Recrystallization will start in some of the grains, not in all grains. So with more and more number of passes, because sample will be rotated in ECAP, so some grains will be oriented properly in first pass, some other in second pass, some other in third pass, like that it will be. So with more and more number of passes, deformation is extended to all grains and recrystallization will be completed, provided there is no cracking. That is an important thing. You have to eliminate cracking or any other such defect. Then we can get complete recrystallization even in magnesium alloys. So how to get that? We have to change the parameters, either chemical parameters, composition parameters, or you have to change the processing parameters. So that we have listed here. What are the parameters we can change? But finally, it is possible to get reasonably homogeneous recrystallized grains after ECAP. Okay, so this is one of the challenges and opportunity. Both are there. The challenge is to get the homogeneous microstructure after recrystallization. But then opportunities, you can get this by changing number of passes with the precaution that cracking should not happen during any of these passes. Okay. Any question or any discussion till now? So if you want magnesium alloy to be used in lightweight applications like aerospace applications or so on, then requirement is increase the strength without reducing the ductility. So strength we have seen, at least in some of the components where size is small, we can go for ECAP. Strength can be increased. But then we don't want any reduction in ductility because toughness should be there. Now how to do this? Once again, there are three methods being explored. One is ECAP, differential speed rolling, other one is accumulative roll bond. So these are the three severe plastic deformation methods used in this direction, so that ductility is maintained. In general, when strength is increased, ductility is reduced. So there is always a balance between strength and ductility. So that's how you manage in small heat treatment of steels like quenching and annealing. So annealing will have higher ductility, strength will be reduced. Whereas quenching will have more strength, ductility is reduced. It's always a balance of these two parameters. But in the case of magnesium, it is not that straightforward. So in the case of magnesium, if you want to increase ductility, you have to ensure that slip in basal plane is activated. So if you have slip in basal plane is activated and ensure that grain is small, ensure that the grain is either ultrafine scale or nanoscale, slip is activated. And if texture is less, so it should not be that all the grains will be oriented in only one plane, only one direction. Different grains will be oriented in different directions. So in each grain, you activate slip in the basal plane, then ductility could be increased. But then when texture is reduced, you have to compromise some amount of strength. So always there is an opposite parameters coming into play. But then to reduce the strength, again you can to balance the strength reduction, you can go for nanoparticle dispersion. That is what we are talking about, precipitation hardening. Precipitation hardening. That is one way. The second way is bimodal grain size distribution. Instead of having single size grains, uniform single size grains, go for some coarse and some fine grains. That's the bimodal grain size distribution. Now, if you see this one, this is the AZ31 and magnesium gadolinium alloy. This is magnesium gadolinium alloy. This is AZ31. This is a static recrystallization. That means initially work hardening or plane strain deformation, quenching, then annealing. So this is separate. Dynamic is as material is undergoing deformation, compression, it is subjected to recrystallization. This is separate. Now, if you do the separate things, you can see here it's only 10 to 20% recrystallization. So the amount of strain is very, very small here. Temperature is same everywhere, 400 degrees Celsius, sorry, 450 degrees Celsius. Okay. So here on the left side is the plane strain compression condition. Plane strain compression condition, temperature and strain. So the change here is increase in strain 0.001, 0.1 and 10 per second. Unit is per second. So you can see large amount of strain rate here. Other things are same. But when you do a recrystallization of that, you can see here after recrystallization, these are all the fine grains. But still, it is not complete recrystallization. This is fine, this is coarse. So this is a bimodal distribution. So this will produce slightly better strength, slightly better ductility. So this is the coarse grain after recrystallization. This is fine grain after recrystallization. So this is a map showing textures. Broadly, you can consider how much percentage of grain is oriented in this direction, like that. So each one has a HKL values. Okay, this is a normal direction here. Based on the normal direction, you consider what is the HKL value. Now here, maximum is at this point. You can see the scales here. The top is maximum. So at the center, it is 5.2%. So out of 100 grains, 5.2 is having this texture. So this number is less than that. So you can find out exact number here. So how much is oriented in this direction. So like that, you can find out texture distribution in this part. But you can see here the weakening of texture. That means the grains are oriented in different directions. If we can activate basal planes in each grain, then slip is possible. The ductility is possible. So here it is, texture is reduced compared to initially, but within these two, this is relatively weak. Texture component is weak in both, but within this more so in magnesium gadolinium alloy. So this can be easily deformed. There is a loss in strength, but then you have to compensate using other strengthening mechanisms. That is the opportunity. So we talked about fine size grain, then ductility, how to maintain ductility. One is bimodal distribution. Then recrystallization during severe plastic deformation in magnesium alloys. So there is a method called as discontinuous dynamic recrystallization. So recrystallization could be static or dynamic. Static is first deform, cool it to room temperature or quench it, then heat it separately. That is static recrystallization. Dynamic recrystallization is as material is being subjected, material undergoes recrystallization and grain growth. Now the discontinuous grain dynamic recrystallization is under narrow conditions, certain part of the microstructure undergoes dynamic recrystallization. It is not the everywhere happening. That's why it is a discontinuous. So it happens only at the original grain boundary. Discontinuous dynamic recrystallization happens at the original grain boundary. Suppose you have a grain size of 60 or 80 micrometers, close to the initial grain boundary, this dynamic recrystallization takes place. Then only it is a discontinuous, which means near the grain boundary we can have fine grains, away from the grain boundary we can have coarse grains. Now the DDRX, which is a discontinuous dynamic recrystallization, is found in many materials, especially materials with low to medium stocking fault energy. So you may be knowing that stocking fault is basically you have arrangement of, suppose you consider FCC, one layer, second layer, third layer, like that. So stocking fault is basically A, B, C. One of the layer is missing in this arrangement. So I have, suppose this region is missing. This is A, B is missing now, here there is no C. So this region is faulty region. This is the stocking fault. So you have one dislocation here, another dislocation. Between them there is no material. So this is the faulty region. So the stocking fault low or high basically depends on energy of this region. Especially low or high basically depends on energy of the dislocation. Each dislocation has an energy per length. So this region is a faulty region, which means it will have more energy. So I can find out area between these two. If I know the length in this direction, width in this direction, I can find out area. So energy by area will give me stocking fault energy of the material. So different materials will have this value different, energy of the dislocation different, which means stocking fault energy will be different. Now if you see the number here, so magnesium is not very high like aluminum, but not very low like copper. Yeah, anyone question?
No questions, sir. Please continue.
Okay. So we said magnesium is having less number of slit systems, so lack of easily activated slit systems. That is supposed to be region for dynamic recrystallization. Now please remember, when the width of the dislocation is small, area will be small, which means energy will be, stocking fault energy will be high. So it can easily move from one place to another place under the action of external force. When width is small, energy is high, it can easily move from one place to another place. So stocking fault movement in copper is different tendency, magnesium is different tendency, and aluminum. So my mobility will be different in each case. But when they move from one place to another place, they can come in contact or very close to the vicinity of grain boundary. So when they come very close to grain boundary, you can have multiple dislocation coming like this. So this region will act as a nucleation for recrystallized grains. So when it happens at multiple places, so initial grain boundary, new grains, recrystallized grains. So like this it will happen. So nucleation of fine grains will happen very close to the grain boundaries. So it will be replaced by fine recrystallized grains. Grain boundary will be replaced by fine grains. So the result is that we have an array of necklace-like structure indicating new grains in the place of original grains. So you can see here, so necklace-like structure is there. So with more and more deformation, I can have more and more new grains. This is what is happening, coarse grain and fine grain. So this is possible when initial grain size is large because if grain size is large, then only you can have unrecrystallized region like this. Now, if grain size is small, you can see here the new recrystallized grains will be touching each other. Suppose grain size is small, initial grain size is small, there will be recrystallization here. So it will happen everywhere. Then this side and this side will be touching each other. So this region is completely filled with the new grains. Whereas when grain size is large like this, there may be new recrystallized grains like this, but then there is a space here which is not with the new grains. So that space is here. So there is a critical size called as DC. It indicates critical grain size required for achieving homogeneous fine grains. So this is homogeneous fine grains. All initial region is covered with the new grains, fine new grains. Whereas this is old grain without change. This is new grains, fine grains. So this is greater than DC, D greater than DC, or very high greater than DC. This is D equal or less than DC. This is the critical size required for homogeneous nucleation. So that is what we are trying to say. Initial grain size is an important parameter in deciding the possibility of fine grains uniformly in the material. Fine grains uniformly in the material. Okay. So this is explained in the words once again. D is less than DC, non-homogeneous structure. D greater than DC, homogeneous structure. Now, how to overcome this problem? When D is greater than DC, we get non-homogeneous. But if you want fine recrystallized structure, you have to make the initial size smaller. So you have to do extrusion E-cap combination. This is only one E-cap is sufficient, whereas here you need extrusion E-cap combination so that the coarse grains will be reduced. That reduced grain size is used for E-cap process to give finally uniform grain size. So you can manipulate microstructures like this. So this is that is the one methodology. This is the second methodology to get the small grains on the grain boundary. So this is actually concept, second theory, not a different procedure. It's a second theory to get this one. This is called as strain induced by boundary migration. What happens is, suppose I have an initial grain boundary like this. Suppose initial grain boundary is there. So this is the initial grain boundary. Now when you subject this material to strain, so there will be lot of strain accumulated at the grain boundary because dislocations will be moving and they will be piling up at this region. So this will happen on the basal plane of the FDP structure. So the result is that instead of having a uniform this one, try it like this, some region will undergo bulging. So this region is bulged. So one region, this is strained region, this is non-strained region. So the boundary becomes like this. So this is the bulged region in the grain boundary. Now with further deformation, this region becomes a link with the help of new dislocation. So there will be a low angle grain boundary. They will be aligning like this. So this is a small grain. It will happen in multiple places. So I have small grains getting accumulated or getting formed at the grain boundary. So this photo shows the bulged grain boundary. This photo shows small grains getting accumulated along the grain boundary to form necklace-like structure. Okay, this is a accumulative backward extrusion process. that sketch we have seen earlier. But thing is that I can have one set of fine grains with the center without having recrystallization. But if I make this a small grain, the necklace at the grain boundary can touch each other, this side and this side can touch each other, provided this is small, less than DC, then everywhere I will have a recrystallized structure. So you may be knowing that shear banding is there. So suppose I have a material like this, I am subjecting to tensile deformation. The deformation is limited to formation of bands like this. So slip is limited to only this plane. So this is a flow localization. Normally flow localization is not desired because it will create what is called as necking in the material. So flow localization is deformation only in certain region, it will be necking. But if material is undergoing work hardening, so this can be delayed or this can be minimized. So when you minimize this local deformation, other part of the material will deform. So uniform deformation is possible provided material has higher work hardening ability. So I will change the chemistry of material by small change in alloying additions. So work hardening ability is changed, which means I can delay this necking or uniform material deformation is possible. So if you see this photo, this is a flow localization or shear bends. This will lead to fracture. So not a desired. I have to eliminate this possibility. So this is another micrograph. Sorry. This is another micrograph. You can see the shear band or flow localization. So flow localization will lead to fine grain formation here, but later it will lead to cracking. Now if you want uniform recrystallized grains, you have to manipulate this shear banding. So instead of having shear banding at only one place, you ensure that shear bands will be happening in multiple places. So diffuse shear bands. So everywhere you have fine grains because there will be multiple shear bands. Everywhere its material will undergo deformation leading to fine grains, grain refinement. So we get a microstructure including fine grains everywhere. So this is possible using what is called as accumulative or accumulated backward extrusion process. So I will get final grain after this severe plastic deformation process. So this is another micrograph showing fine grains in magnesium alloys. So these are all extremely fine grains. So 500 nanometer scale, this is much less. It is not guaranteed that everywhere it will be same size, but we are showing some of the regions where fine grain is possible. Because TM gives only information on a small sample. Twinning is another mechanism. Twinning is another mechanism. It can be used for grain refinement. So in magnesium or in general CP based material, twinning tendency is a direction dependent tendency. The stress required for tensile twinning in magnesium alloy is about 2 megapascal, whereas for compressive twinning under compressive stress conditions is about 114 megapascal. So what you feel is, since stress is low for a tensile twinning, it is common, whereas compressive twinning is generally not observed under normal conditions. But when you do ECAP, at certain locations, stress will be very high, it will be compressive because ECAP is a multiple stress from multiple directions. So though you press from one direction, because of the constraint in the form of die material, there will be multiple stress components. So under ECAP, both compressive tuning and tensile tuning is possible, and they will happen in different directions. So that will lead to grain fragmentation. So this microstructure shows twinning in the material. It's in a tensile twinning happens at a lower stress, whereas the next one shows multi-path directional forging, so extremely fine tuning. Extremely fine tuning. Scale is 2 micrometer here, so this is much smaller than that. So this shows by doing this we can change mechanical properties like fatigue resistance of the magnesium alloy. Okay. So with this background, how to get uniform recrystallized grains, how to maintain ductility. So we'll move on to a new processing method, which published in scientific reports. So it is called as hard plate rolling of magnesium alloy. So if you use normal rolling for magnesium, the deformation tendency here will be different, deformation tendency here will be different, deformation tendency here will be different. That happens because though you apply compressive stress here, because of the geometrical conditions here, there will be shear stress, and shear resistance or resistance for shear stress will be different at different points over the cross section, which means material is non-homogeneously deformed. When initial grain size is large, this non-homogeneous deformation will lead to defect like cracks. So that is not desired in a magnesium rolling. So for this alternative is hard plate rolling. So hard plate rolling means I am using two hard plates and between them I am putting a sample. So this is not directly touching the sample because it is through this hard plate which is non-deforming type. The stress on this material, stress over the cross section of this material is homogeneous. So homogeneous deformation takes place. So this is initial microstructure. You can see large microstructure. This is a 10 micrometer scale. So this may be 30-40 micrometer cross section, and this is the second phase, magnesium 17, aluminum 12. This is a texture map or orientation imaging microscopy. So you can see the texture here. Some amount of texture is weakened on the elongated direction. So otherwise everything is focused here. You can see the texture. So slightly weakened structure, basal structure because of the extrusion. So after hard plate rolling, we can see extremely fine particles both on the boundaries and inside. Both on the boundary and inside, particles will be extremely spread. So particle strengthening is possible. Now if you see the scale, this is a very extremely fine scale. Okay, this is fine scale, 5 micrometer scale. So the particles will be 1 or 2 micrometer, whereas this boundary is a large grain, coarse grain. So coarse grain, fine grain, both are possible after hard plate rolling. So number of grains, especially here given, distribution of grains, fine grain, coarse grain. So this is a strictly a bimodal distribution of grains. Now number of grains and their textures. So this is rolling direction for small grains, this is for the coarse grains. So you can see this is distributed, whereas this is along the normal plane, basal plane. So this is a distributed texture. This is compared to this, it's a texture at the basal plane. So if you do EBSD, electron backscatter diffraction, you can see fine grains like this and coarse grains, and the corresponding orientation will be there. So basal plane is parallel to the rolling direction. The number of unit is about 24%. Number of crystals is about 24%. You see this one, it is not exactly at one point or the center, it is spread. So micro texture is weakened texture. This is relatively strong texture, this is relatively weak texture. You can see 24% in the coarse particles along the basal plane, this is only 8.2%. So after recrystallization, texture component is slightly weak. But then we can have the second phase particles. We can have second phase particles both on the grain boundary and interior. They will contribute for increased strength. So we can also see the misorientation, that is the grain elongated along this direction and orientation between nearby grains, misorientation. So you can see 20 to 30 micrometer, there is a lot of misorientation with the neighbors. So they are elongated along the rolling direction, whereas here it is a gradual change. Now if you see the TM micrographs, you can see ultra fine grains here, and grain boundaries are not sharp. And if you do mechanical testing to determine strength and ductility, you can see here the material is having about 25% engineering strain. For magnesium, it is very good number. The strength is about 350 or 371 MPa, and work hardening exponent is 0.27, which means necking will be delayed in this material. Now compare this with the as-cast AZ91. Tensile strength is 250, so it is 60% of this material, and elongation is 5 to 10%. Here it is 25%. And in a conventional extrusion, elongation is 15%. Tensile strength is 350. So this 370 is close to 350, but we have very high elongation in the SPR sheet. Now this is showing other type of hard plate rolling against other types of severe plastic deformation. So hard plate rolling is, here it is there. DHPR is basically dual hard plate, two stages of hard plate rolling. So this is much better both from elongation point of view as well as UTS compared to all other materials. Okay, UTS may be very close to that or slightly less, but elongation is much better. So we are about to wind up because time is also over. So heated hard plates between the rolls and magnesium sheets can overcome non-homogeneous deformation of magnesium during rolling. Using this hard plate reduces heat dissipation from the sheets to the rolls, which reduces cracking. Remember, hard plate is heated hard plate. So use of heated hard plate reduces cracking tendency in the rolling. Now the shear stress applied on the sample during rolling partially gets converted into normal pressure because plates are hard. It promotes larger thickness reduction and increasing rolling efficiency. So all these things will help better compared to other types of SPD processes. So some of the conclusions from this discussion would be, working with magnesium alloy is difficult always, no doubt, compared to aluminum or copper because it's a hard metal, which means number of twist system will be much less. But it is possible to get good microstructure by fine tuning the parameters, and once we get a good microstructure, naturally final properties is much better. So even nanostructures is also possible. So this is a very good domain for working, and if you can make into industrial scale, no doubt it will be a premier material, premier structural materials in lightweight application. So that will be the end of my talk. And once again, thank you all for patient hearing. Thank you, organizers, everyone.
Okay.
I know at the end it is becoming a strong or more, what you call, abstract, but sometimes you have to expose so that many of you may be doing research and you can think in this direction to solve some of your problems. Yeah, please, over to organizers.
Okay, sir. Thank you for this session. Participant, now we are open for Q&A. Rajat, sir, it's over to you.
Yes. Thank you, Dipankar. Sir, good morning, Uday Bhatt, sir.
Good morning, sir.
Uday Bhatt, sir, is my professor and former HOD of Material Science Engineering at NIT Surathkal. He is a very experienced and excellent researcher. He has got many funded research projects. To name a few, under Department of Science and Technology, under FIST, he has funding for transmission electron microscopy and transmission electron microscopy preparation unit, which is around 5 to 6 crores. Many such research infrastructure he is having through various funding agencies. And whenever we approach for our students, researchers, to do various experiments at NITK, he really agrees and helps a lot. So I would personally like to thank him, and it is very difficult to catch Uday Bhatt sir to give a talk, because normally he's a very, very busy man. But he couldn't deny me, because I am one of his students. So in that way,
Thank you, Hedde. Thank you, Dr. Hedde, for your nice words and presenting here. You reminded me one thing. I will take 1 minute for audience benefit. All the friends, we have a central research facility which is now almost getting installed. Okay, we have about already 35 equipment, and another 30 equipment will be there. Totally 70 equipments will be there. About 35 equipments are installed. So many research tools are available. You need not run around to multiple places. All these are open to any citizen of India on a payment basis. You may have to give a nominal payment, but facilities available. Many of your research work, your students' research work can be carried out, and NITK will be very happy to give a service for any Indian citizen. Okay, if anyone needs information, you can contact me what type of tools, or you can write to Chairman CRF, Professor Satyanarayana, who is my friend, is the chairman now. I was heading the CRF till last month, now Professor Satyanarayana.
Thank you, sir. Okay. Thank you. Thank you,
right.
Sir.
Right, sir.
Over to you, Dipankar.
Thank you, sir. Again, participants, if you have any question, please raise hand or you can write it on chat box. Dr. Pankaj Kumar Singh, now you can go.
Yes, sir. Thank you, sir. Myself, Dr. Pankaj Kumar Singh from ITBHU.
Right, sir. Good morning.
Your lecture was very nice, sir, as interactive also. My question is that there you have used one JK60 alloy and JD41 alloy. Can you explain both of these?
Which alloy?
ZK alloy and the ZE
alloy. Sir, that is information taken from the net. We have not used it. And most of this information we have collected from other this one, except the mechanism. Okay, we from at NITK we have worked on ECAP of aluminum alloys, various aluminum alloys. Magnesium we have started only. Magnesium details are not there. So ZK alloy, if you ask me microstructural information, I have no information more than that.
No, sir, but 8Z, that is the aluminum and the zinc. Likewise, what is this K and E?
Oh, that much I can tell. I have shown it. Okay, I will 1 second. 1 second. It is there in one of the slides I have displayed. K is zirconium, if I remember. K is zirconium.
It is zirconium only.
K is zirconium, E is rare earth.
Yes, sir.
E is rare earth, K is zirconium.
Okay. Rare earth. Which rare earth?
There are many rare earth elements. One of them maybe I think yttrium is coming under rare earth.
K that is
K is zirconium.
zirconium.
K is zirconium.
Okay.
K is zirconium. And there is one thing which I did not mention is if they are in the first position or second position, sometimes there is a changes in the nomenclature. Okay.
Okay,
Right.
sir.
Right.
Okay, any more questions? Participants, you can either raise your hands or you can write it on the chat box. I would direct it towards the speaker. Okay, sir. If participants, if there are no more questions, then we would wind up this session. Thank you very much, sir, from the whole team, from the whole FDP team, from the organizer team. I humbly thank you, and it was a beautiful session on how exactly research should be taking place and what are the experimental methods that can be taken when analyzing these methods. So it was very much informative and very precise as well. I again thank you from the whole team. And dear participants, we will break for around short time and we will come back at 11:45 sharp for the next session. Thank you very much, sir.
Thank you, Dr. Hegde and all your committee members.
Thank you, sir. Thank you.
Thank you. We hope to see you physically now onwards.
Yes, sir. Yes, sure, sir.
Right. Bye.
Thank you, sir. Thank you. Bye,
So
sir.
I'll take a break. Thank you, everyone.
Bye, sir. Sure, sir.
Thank you, sir. Thank you. Dear participants, we will rejoin the meet by 11:45 for the session number 2 of the day. So we'll take a short break and I ask your humble self to be on time. Thank you very much.